When you build a basic prototype for a video platform, the first instinct is to push the raw video upload directly through your main server. But when a user drops a massive multi-gigabyte file into that pipeline, the sheer volume of data immediately saturates the server's network capacity. In a theoretical happy path, that single server handles everything in perfect order, accepting the upload, updating metadata, transcoding the file into a streamable format, saving it to disk, and pushing it to a CDN. The vulnerability here is the linear execution. The system processes each stage sequentially. If the transcoding step takes 20 minutes to encode a high-definition video, the entire server is blocked from handling new requests until that job finishes. Under production-scale stress, this architecture breaks in 3 distinct places. First, the API servers drown under the weight of incoming binary data. Second, the processing workers deadlock while waiting for upstream tasks to finish. And third, pushing every processed video to a global CDN causes bandwidth bills to explode. To survive the transition from a fragile prototype to a production environment handling thousands of concurrent uploads, we have to redesign how the system manages stress. We need an architecture with 4 specific mandates. It must execute tasks in parallel, remove the API servers from the upload path, secure the copyrighted assets, and aggressively restrict bandwidth consumption. Scaling to this level relies on the specific way data flows and waits within the system, bypassing the performance ceilings of individual server hardware. Routing a gigabyte-sized binary stream through a standard stateless API server instantly consumes its available network input and output. The server spends all its time reading and writing a single file, dropping other incoming requests. To restore throughput, we remove the API server from the data transfer, delegating heavy lifting to a storage bucket. The flow begins with the client sending a lightweight HTTP request, simply asking permission to upload. The API server responds by generating a pre-signed URL. This is a cryptographic token that grants temporary direct write access to a very specific location in the object storage. Once the client receives this pre-signed URL, it uploads the heavy video file straight into the storage bucket. The binary data completely bypasses our application servers. Because the API server never handles the massive payload, its network bandwidth is preserved for routing traffic and executing core business logic. We bypass the API, but we don't bypass security. The pre-signed URL ensures that the client can only upload to the exact path we specified, and the token expires after a short defined window of time. By cleanly separating the authorization layer from the actual data transfer layer, we eliminate the upload bottleneck entirely. Once the video lands in storage, we face the chaos of user inputs. Files arrive in unpredictable formats, codecs, and resolutions. Every single upload must be standardized into a uniform format before a player can stream it. If a worker node runs a sequential script, extracting audio, then converting video, then generating thumbnails, it wastes immense capacity. The CPU sits idle during I/O operations, and the time to publish stretches out. This chart illustrates the fix. We replace the rigid script with a graph of discrete, independent tasks. This execution model is a directed acyclic graph, or DAG. A DAG scheduler analyzes the required jobs and runs them sequentially only when one task strictly depends on another. If tasks are independent, it runs them in parallel. In the initial pre-processor phase, the source file is split, generating separate branches for video, audio, and metadata. Downstream workers then tackle these isolated branches simultaneously, encoding video and audio at the exact same time. This structure also allows us to inject mandatory steps, like applying a visual watermark or running a quality validation check, running concurrently alongside the standard encoding process. Adopting a DAG model transforms a slow, linear script into a parallel execution web, reducing the total time to process and publish an upload. Even inside a DAG, a structural vulnerability remains. If one stage hands its output directly to the next stage, a slow downstream worker forces the fast upstream worker to sit idle and wait. This diagram shows how we prevent blocking. We introduce message queues as asynchronous buffers between pipeline stages. An upstream worker finishes a task, drops an event into the queue, and grabs a new job without waiting for acknowledgement. The downstream consumer operates on its own schedule. It independently pulls the next job from that queue only when it has the free compute capacity to actually process it. The core benefit is physical decoupling. If an encoding worker crashes, the download worker doesn't freeze. It just keeps dropping jobs into the queue until the encoding pool recovers. These queues also enable highly granular autoscaling. The system constantly monitors the exact depth of pending jobs in every individual queue. If the thumbnail queue sits empty, those specific worker instances are spun down to save money. If a massive wave of uploads causes the encoding queue to bulge, the system instantly spawns new encoding workers to absorb the surge. Message queues act as asynchronous buffers. They allow every step of the pipeline to scale elastically, immune to the failures of its neighbors. With the processing pipeline decoupled, we face the final and most expensive hurdle: serving massive, high-definition video files to millions of viewers globally. Before any distribution occurs, we have a strict security mandate. The assets require digital rights management integration and AES encryption, establishing a fixed compute cost to protect creator copyrights and prevent unauthorized downloads. The massive financial threat emerges during delivery. Pushing every single encoded version of every uploaded video to premium, global edge content delivery networks will quickly bankrupt the platform. This chart maps our infrastructure to long-tail distribution. We cache the highly viral, popular videos on expensive edge CDNs to guarantee zero latency. But for millions of rarely watched videos, we bypass CDNs, serving them directly from cheaper origin servers. For the extreme tail of entirely unwatched content, we save massive storage costs by keeping only the raw file. We encode those specific videos on demand only if a user actually clicks play. Achieving profitability at scale requires acknowledging that not all data is equal. A sustainable infrastructure must map directly to economic consumption patterns. In any large-scale distributed system, hardware fails, network packets drop, and errors are unavoidable. The architecture must handle failure gracefully. For recoverable errors, like a failed transcoding segment due to a network blip, the system relies on automated retry loops with exponential backoff. When a job fails repeatedly and becomes unrecoverable, like a corrupted video file, it gets routed to a dead letter queue. This is a secure holding area for poison jobs, guaranteeing that bad data won't continuously clog the main pipeline. Safe completion handlers are equally critical. When a task finally succeeds, these handlers ensure the metadata database is updated accurately, preventing duplicate ghost records or out-of-sync states. To maintain this equilibrium, the engineering team relies on specific dashboard metrics, monitoring queue depths, tracking worker saturation, and measuring CDN hit ratios. Managing a platform at this volume requires looking past the simple act of playback to the infrastructure orchestrating it. The final system is a parallel, cost-aware pipeline that standardizes unpredictable uploads and absorbs frequent system failures, ensuring that global distribution remains financially sustainable.